All right, let's get right into it. Today, we're building our essential toolkit for crushing calculus, the limit laws. Think of these as the rules of the game that let us take apart even the most complicated-looking limits piece by piece. So you might be wondering, why is it that some limits are just super easy, a piece of cake, while others feel like you've hit a total brick wall? Well, it all comes down to how a function behaves right at that specific point we care about.
And check this out. This slide shows you exactly what I'm talking about. On the left, you've got a simple case. You can pretty much just plug in the number and you've got your answer. But look at the one on the right. If you try to plug in 3, you get 0 divided by 0. And that's undefined. Now, this doesn't mean it's impossible. It's actually a signal, a clue, that we need a smarter strategy.
So here's our game plan. We'll start by looking at those easy versus hard cases. Then we'll lay down 2 super foundational rules. From there, we'll build out our entire limit law toolkit. Then, I'll show you an awesome shortcut that comes from these laws. And finally, we're going to learn how to tackle that tricky 0 over 0 problem.
Okay, first things first. We've got to lay some groundwork. Let's start with the 2 most fundamental rules you'll ever need. These are the absolute building blocks for everything else we're going to do.
Now, what's so great about this slide is just how simple and intuitive these rules are. Rule number 1. The limit of x as x gets closer to some number a is, well, it's just a. Makes sense, right? And the second rule is even easier. The limit of a constant, c, is always just c. I mean, a constant is a constant. It doesn't care what x is doing. These 2 ideas are our foundation.
All right, with that foundation solid, it's time to build on it. This is the main event, your limit law toolkit. These are the powerful rules that let us deconstruct those big, messy functions into the simple, bite-sized pieces we just talked about. And here it is. The core idea behind all of these is actually pretty amazing. You can basically push the limit operation inside the problem. So the limit of a sum is just the sum of the limits. Same for differences, products, and so on. There's one huge exception to watch out for, though, the quotient law. You can't have the limit of the bottom part, the denominator, be 0. That's a big no-no. Let's actually see how this works. We've got this rational function, right? First, we hit it with the quotient law to split the top from the bottom. Then, we use the sum and difference laws to break those parts down even more. Finally, the power law and our basic rules let us solve every little piece. We put it all back together, and we get our answer, 1/4. See? Systematic. Now, after going through all that work, breaking things down step by step, there's a fantastic reward, and it's a huge time saver. Let's talk about the direct substitution shortcut. And here's the big insight. For most of the functions you see every day, polynomials and rational functions, you can actually skip all those individual laws. As long as the number you're approaching, a, is in the function's domain, meaning it doesn't break the function, you can just plug it right in.
And this is a perfect example of that power in action. We want the limit as x approaches 3. Does plugging in 3 make the bottom 0? No, so it's in the domain. We just substitute 3 in for x, do some quick arithmetic, and bam, there's our answer, 10 over 19. So much faster.
But what happens when that beautiful shortcut fails? What do you do when direct substitution gives you a total disaster? This brings us to the main event. How do we solve the dreaded 0 over 0 problem? This is the warning sign. It's called an indeterminate form. And it's really important to know that it doesn't mean the limit is 0 or 1 or even that it doesn't exist. It's a clue. It's telling you that there's some hidden algebra going on, that something needs to be canceled out, and our job is to find it. So when you see this, does it mean the problem is impossible? Game over? Absolutely not. It just means the function has a little hole at that exact point. Our job is to use algebra to peek around that hole and see what value the function is getting closer and closer to. So here is our 3-step battle plan for these kinds of problems. First, always confirm that you actually get 0 over 0 when you plug in the value. Step 2 is the most important. You've got to use your algebra skills, factoring, using conjugates, whatever it takes to rewrite the function. And finally, you can use direct substitution on that new simplified version.
Okay, let's take on our first challenge. This is a classic problem that needs factoring. And as you can see, if we try to plug in x equals 3, we get that telltale 0 over 0.
So here's where the algebra magic happens. We factor the top, we factor the bottom, and look what happens. An x minus 3 term pops up in both places. That's the culprit. That's the term causing the zeros, and now we can just cancel it out.
And once that problem term is gone, we're left with a much simpler function.
Now, this new function is identical to the old one everywhere except at that one little hole at x equals 3. So now we can use our direct substitution shortcut. Plug in 3, and we find our solution. The limit is 3/7.
All right, let's try a different kind of problem. This one's got a square root, which often means we need a different tool. And again, if we try plugging in x equals -1, we get 0/0. The technique we need this time is called multiplying by the conjugate.
Now, conjugate sounds like a fancy word, but the idea is simple. You take the expression with the square root, and you just flip the sign in the middle. We multiply both the top and the bottom by this conjugate, and what it does is pretty brilliant. It gets rid of the square root on top and reveals the hidden term we need to cancel.
So after we multiply and simplify the numerator, an x plus 1 term appears, and that cancels perfectly with the x plus 1 on the bottom. With that gone, we can safely plug -1 into what's left over, and we get our final answer, 1/2.
And for our final challenge, we've got a complex fraction. Yup, a fraction inside of a fraction. It looks like a mess, and, surprise, surprise, plugging in x equals 1 gives us 0/0 all over again.
The strategy here is all about algebraic cleanup. We find a common denominator for those little fractions up top, combine them, and simplify the whole thing. Once we do that, the hidden x minus 1 factor reveals itself. We cancel it, plug in our value, and we get the solution, -1/4.
So there you have it, a whole toolkit for handling limits, from the easy direct substitution cases to the algebraic tricks for that 0/0 form. And that leaves us with one final thought to chew on. Now that you have this powerful toolkit, what kinds of functions do you think are still out there that might break these rules?